tomorrow. So I look at the homework from 3.2. So here they want you to integrate the function, really basic one, 5, in the region between e to the x and x plus y equals 4 in the region x from 0 to 1. So you graph it, and in some ways, in graphing it, you'll see why I probably don't like things like e to the x, even though e to the x is something you should be able to graph. So not to scale, but there's e to the x. Here's x plus y equals 4. So this, for example, is 0, 1. This is 0, 4. And it says from 0 to 1. So normally I would just say get the enclosed region, but here that would be a pain because unlike quadratics and linear, which I assume you can solve, if you set these two equal, so if you plug in y equals e to the x, you get x e to the x is equal to 4, which doesn't really have a nice way of solving except for getting estimates using some method. So I like having you solve, which means I tend to do quadratics and linear. Okay. So here it says integrate this, so it's really a simple one, just the 5. And let's set it up both ways. So let's start with dy dx, and then I'll also set up doing it dx dy. And you'll see that there's one more point that you'll need. Yeah. Okay, so for the limits, obviously x goes from, so the outside limits are 0 to 1, and the inside limits are, and so here we're looking for the bottom function, the top function, because we're doing dy dx. So the bottom function is e to the x, and the top function is solving x plus y equals 4, gives 4 minus x. Okay. So there's dy dx. And now let's do the same thing. And I'm going to need more room. Dx dy. And so the first question is, can I do this with one integral? Let me make it more obvious what my region is, so I put that there. No. Can I even do it with two integrals? Yeah, so we're going to need 3 of them. So we're going to need to get these points. This one's easy. This is the point x equals 1 and y equals 3. This is the point x equals 1 and y equals e. So I should have made my graph bigger, but you can kind of see here's one region, here's another region, and then the top third region. So in this lower region, first, where is that true from? So where does that range from? So the outside limits for y would go from, and you can also see my thing is not to scale. Okay, so that would be this one, which is fine. So If I start at the bottom one, it's going to be 1 to e, as a couple people said. And for that one, the left limit is that's going to be the right limit, the upper limit. Because as we saw, get x equals ln y. So it's going to be in the top. And the bottom, it's going to be 0. And then we'll plus. And then another plus. So now we're in the middle one. So in the middle one, yep, it goes from e to 3. As I said, not to scale. And here, oh, so right here. So we had the right function is y equals e to the x, which we have to solve in terms of x to get x equals natural log of y. Right, so in some ways, I'm kind of pointing it to here, which is this is the right function. I really should, if I bring it up here, and it's a bit more obvious. Because then here are the two things. So for the middle one, what are the left and right? And this one actually isn't bad. It's just 0 to 1, because it's just a box. So that's an easy one. And finally, as Keen said near the top piece is from 3 to 4. And now the right, getting very messy. Now the function on the right, so the function on the left is still 0. The function on the right is now 4 minus y. So this whole thing. So if you're actually doing it, pretty obviously you wouldn't want to do it that way, but it's good practice for setting up because you can see all the little pieces. So any questions on either of these two setups? Okay, so let me jump. One of the things is this section and the next section, there aren't too many where they actually make you draw and, oh, sorry. So here's our picture again. So these are the 3 pieces. And we had that this is the point on E. This is the point 1, 3. Again, not to scale. This is the point 0, 1. This is the point 0, 4. So in terms of y, you can see we have the range. Y goes from 1 to 3. 1 to E, sorry. And then this range, which is e to 3, because we're looking at the y's. And then here, we're going from 3 to 4. And then for the inner ones, remember what we're doing is we are saying what's the left and the right function, because smaller and larger, when we're doing it in terms of x, we draw like this. So I'm looking for what's the smaller and what's the larger. So on the left, I hit the function just the y-axis, which is 0. Wrong place, 0. And on the right, I hit the y equals e to the x. And I have to solve for that in terms of x. In the middle, again, I draw a typical horizontal line. I ask what function do I hit on the left and the right. Here it's easy because it's just the constant 0 and the constant 1. And at the top, if I draw a typical horizontal, I ask what's the left and what's the right. So left is still the 0, and the right is this function x plus y equals 4. And since we're solving for x, we get 4 minus y. So you're looking at what is the function I hit in the left, what's the function I hit in the right. Is that okay? Okay, so now let's jump to 28. As I said, there aren't too many that are done well that you have to do much with, but let me look at this one. So it says here we have this, and what they want you to do is to draw the region and then reverse the order. So we'll get this in terms of dx dy. So we kind of draw all the pieces. Oops, that's why I said 1 minus x. That's supposed to be, I don't know if that was me being silly or it trying to write trying to figure out what I wrote, but it should be natural log of x. So I draw y equals natural log of x. Looks like that. Going through the point 1, 0. I draw y equals 2. And you'll notice that this is the point e squared 2. So we can see why we're going from 1 to e squared for that first one. And then the first integral says we're going from 0. So I draw the 0. And I draw the 2. Y equals 2. So this rectangle is the piece I get from that first integral. So this whole thing is the region we want. And as I said, they now want us to rewrite in the reverse order. Okay, so again, the first question is, can I do it with one integral or am I going to split this? So can I do this with one integral? Yes. And the answer is yes. Okay, there we go. I always have to remind myself that there's always a delay, so I have to give yourself a bit more time than I would in class. So, therefore, I can do it with one integral, and I'm looking again, draw a typical horizontal line. What are the two functions I hit? So on the left, it is x equals, I should put it, this is y equals ln x. So on the left, it is 0, and on the right, it is kind of backwards of the one we just did. So y. And the limits. So it could be 1. So we could break it up into two pieces like we did for the first part. We don't have to. And now the limits for y are 0 to 2. Yep. And so that would be the same thing. So any questions on this? Okay, so let me do one more. Although, let me wait a second. As I said, think about the lag. Okay, so now let's look at one more. Just the next one, 29. Again, one where we're going to rewrite. This one for a different reason. So this one is only one integral, but I look at it and the first part asks me to find the antiderivative of cosine of y over y squared, which certainly isn't an obvious one. So I might try switching the order to see if I get something better. So this one I'll actually do the antiderivative, all the steps. So as the last one we draw, so we have y equals x over 2. Just the line. We have y equals pi. Just a straight line. And you'll notice it is at the point 2 pi, which means that we have the triangle. So this one in some ways isn't as difficult as set up as the last one, but as I said, I should do at least one all the way through, and this one is one where it makes sense to switch. So if I switch, then again, switch. And again, what's the smaller to the larger function in this case? So what are the limits for the inside integral here? So again, usual thing. Right. Yep. So 0 to 2i, because we're looking for the function on the left to the function on the right, and solve that in terms of x. And then for the y, now we're just looking for what values of y is that true. And so that you can see is 0 to pi. And you can see the reason we want to switch is now the antiderivative with respect to x is much easier, and we're hoping things simplify if we do that. So let's actually do this one. And I'll do one more after this where a bit more of a setup. So here, so obviously cosine of y over y squared is a constant, so I'll bring that along. And otherwise the antiderivative is what? So what's the antiderivative of this with respect to x? So I said I'll just bring along the constant. That'll be just the 1/2 x squared. X equals 0 to 2y. Make the y a bit more obvious in this one. And so I plug in, I get 4y squared divided by 2, so 2y squared. Okay, before I can answer, that works out. So the y squareds cancel. And it is something I can do. And here we do get 0. So first of all, remember, 0 is like any other number, so there's nothing wrong with getting an answer of 0. It's not obvious that that's what it would be, although it's not also not obvious because we're going from 0 to 2 pi. So cosine of y is going through the full cycle, so you kind of accept maybe it will go away. But it's, to me at least, not obvious. But in this case, you get 0. So where the, oh, I don't know where the 2 went. Thank you. In some ways, I think I was just not worrying about it because I knew it was going to be 0, but I should put it in. So any questions on this? Okay, so let me make up another. There aren't too many in the text where you have to do stuff, so let me take one from, I think, one of the old quizzes or quiz reviews or something like that. Another one where we switch the order. A bit more elaborate. As I said, typical quadratics and lines, which I assume you can graph. It's almost a straight line. So let me graph things. So I have y equals x squared equals 4x. So let me exaggerate things a bit. Here's y equals x squared. Let's make that y equals 4x. And then let me put in somewhere in x equals 1. So that would be that first region. And then it says now we're going from x squared to 4. Notice at this point this is 1, 4. So y equals 4 is right there. And this is 0.24. Sorry, my graph is getting messy as usual. And so you can see that the second integral is giving us this region. So first region and second region. And therefore this whole thing is the region we want. Again, I want to reorder. So, same question as the last couple. Can I do this with one integral? Yes. So therefore, I ask what is the left curve and what is the right curve. So draw a typical horizontal line. And I ask what do I hit in the left, what I hit in the right. So I hit 4x and x squared. The only little thing is I just have to solve for that in terms of x. So therefore, it will be x equals y divided by 4 and square root of y. And that is true for y going from, and again, we look at the bottom and the top, which is 0 to 4. Okay, so any questions on this? Right, so those are the ones I want to look at, including the extra one, but any other ones from 3.2 homework that you want to look at? Oh, so sorry. So I somehow lost Gwyneth's question. So the region I'm looking at altogether is that region there. Okay. 23, I don't think the actual setup is too terrible, but does it have ASD? So it's asking us to draw the region, decide if you want to leave it like this, or if you want to, oh, so sorry, yeah, that's a secant x. So draw the region, decide if you want to leave it in this form, or if you want to rewrite it as dx dy. Yeah. So let's draw the region. So we have y equals cosine of, is that right? Okay. I was gonna say that doesn't make sense. You can still do it, but usually you don't put this smaller function on the bottom. So this you wouldn't have to do, although if you have a graphing calculator, it should be fairly straightforward. So cosine of x looks like that. Secant is 1 over cosine of x, so it kind of instead goes up. And pi over 4 is somewhere around right there. So it's this region here. So the first question is, do we want to try it this way, or do we want to switch the order? And so the answer to that question is this. Do you know the antiderivative of that with respect to y? And separately, do you know the antiderivative of that with respect to x? So what's the antiderivative of that with respect to y? Right. So let's try it that way. So that's, at least that first step is pretty easy. So in other words, we probably don't want to rewrite it. So obviously, if I plug in y equals secant, I get secant squared. What is secant times cosine? Right. Secant is 1 over cosine. So obviously the second part is easy. So the question just is, do we know what the antiderivative of secant squared is? And in some ways, probably didn't come up a lot in Calc 2, but it is one of the more basic derivatives in Calc 1, so you should know it, although I probably wouldn't have it come up. Right, it's tangent. still. And again, you can just plug into a calculator, but this should be one you know. What's tangent of pi over 4? Right. Pi over 4, and then tangent of 0 is 0, so this is the whole thing. So I'm not going to have you graph something this elaborate. As I said, pretty much just quadratics and circles and lines. So any questions on this? You can also see that we really wouldn't want to do a dx dy, because what we'd have to do is, first, we'd have to split it because the left function changes. Second, we'd have to solve for x in terms of y. So for example, we would have y equals cosine of x, so x would be inverse cosine of y. And at the top, or the right, it would be inverse secant of y. And don't really want to deal with inverse secant and inverse cosine. Any others? Okay. All right, so let me look at 3.3. Do the same function for two different ones. Let's do this one first. So we have a function, and in some ways, looking at both pieces, this is made for, remember this is polar coordinates. This is made for polar coordinates because we have circles. So polar coordinates are made for circles. So first usual thing, I draw it. Oh, 1 plus x squared plus, yeah, so let me rewrite this. 1 divided by 1 plus x squared plus y squared, all cubed. So this is x squared plus y squared equals 9. Okay, so let me remind you of the pieces, which is the way to go from one to the other. So x is equal to r cosine theta, y is equal to r sine theta, and x squared plus y squared is equal to r squared. So this is made for polar coordinates, so that means that it's going to have nice limits. So here, what are the limits? So r goes from, so there's a typical radius, 0 to 3. That's the origin to the circle. And the angle goes from 0 to pi over 2, because we're just going from the first quadrant. And the 1 plus x squared plus y squared becomes right, 1 plus r squared, and then leaving 3. And then the other part you have to remember is once you change the function from it in terms of x, y to in terms of polar coordinates, we always get r. So this is the equivalent, and that's supposed to be a dr d theta. This is the equivalent of the dy dx. Right. In some ways, it doesn't have to be. As with dy dx, you can always do it whichever order you want. And for constants, it really doesn't matter. But if you start getting functions, I usually find it hard to picture how theta is in terms of r. So I tend to do it r then theta, but it doesn't really matter. And one more. So over the region bounded by x, y equals 2x, circle. Just to be different, let's make it x plus y squared equals 4. I really should say it in the first quadrant, but I'm going to try to fit everything in, so I'll leave that off. Because, of course, if you do the y equals x and y equals 2x, there's also going to be a region over here in the third quadrant. Oh, just pi over 2 is the, right, because we're in the first quadrant. So we're only going as far as the y-axis. So if we did the whole circle, so if I just said over the region x squared plus y squared is less than or equal to 9, then we go 0 to 2 pi all the way around. So here I'll start filling in. So again, we get the same thing inside. So here, what are the outside limits? Start with the easier one. So notice the nice thing about doing lines like y equals x and y equals 2x are they go through the origin. Oh, so, sorry, that isn't the easier one. Sorry about that. The inside limits are the easier one. So let's put the inside limit. Sorry about that. You are correct. That are one, but I'll get that in a second. I'll ask where you got that from. So what are the inside limits? And the reason this is nice, it is just an arc, which means it is the full thing. For the outside limits, we need the two angles. One of them is pretty easy. Y equals x is just halfway through. So that's going to be pi over 4. For the other one, there are a few ways of doing it. One way is you can just put in values for x and y, make a right triangle, and then figure out what theta is. The other way you can do by putting in the two limits. So for example, y equals r sine theta, x is equal to r cosine theta, so it gives me that. And then if I divide through, I get tangent of theta is equal to 2. No, because the inside limits are r. So if I draw a typical radius, notice it goes all the way from the origin to the circle. So for the other one, so yeah, so this is one way of doing it. As I said, you can also draw the right triangle, and then that would give me, this is nothing nice. We can either just leave it as Shin did as tan inverse of 2, or you can actually get an angle. Yes, right. So this is the circle x squared plus y squared is equal to 4, which is telling you that r squared is equal to 4, so r is equal to 2. So the outside limits are the angles. So that's these first angle and the second angle. And at this angle, you can probably just figure it out. Y equals x is just halfway. So since this is pi over 2, and this is 0, halfway is pi over 4. So pi over 4, the angle isn't too bad. And then this is the steps for getting the other one, which is we have y equals 2x. I plug in what y and x are in polar coordinates. The r's cancel. I divide through to get tangent, and then just solve for theta. That's kind of the more elaborate way, which we could also do with the pi over 4 if you didn't see it right away. The only difference is you would get r sine theta is equal to 1 times r cosine theta, so tangent of theta would be 1, and therefore the lower limit is inverse tangent of 1. So, any questions on other questions on this? All right, so I do the Wednesday thing, which is now I will put up the quiz review. As I said, if you want to download it, it's also on Blackboard now under the summer 1 folder. But let me share it. So last chance, any questions on this? Oops. And same as the other couple one, give you 20, 30 minutes. Then we'll go over it, and then we'll continue on with things. You'll notice that one of the questions on number 3 is polar coordinates, and so this is you deciding if that's okay. So this, I got lazy this time. This is the actual, it worked out. This is the actual quiz 4 from last semester. So this will be almost exactly what your quiz will look like with different things, depending on whether we're putting question like 4 in. So let me know if you have any questions, and otherwise I'll just sit here as you try it on your own. Sorry, I went away. So yeah, so for one, yeah, it doesn't matter which one you do. I think dy dx ends up being easier, but whichever one you want. Okay, so let's try it. It's been a bit over 20 minutes. So first let me draw, and then you'll tell me what the limits are. So for 1, get there are the two functions. And we'll need the 2 points. What are the 2 points? So the one on the left is the point. And the one on the right is, and then I'm going to ask you, so if you don't see that, or what you would do is you would set them equal. And then to get this quadratic, bring everything to one side, and then factor, or use quadratic formula. So therefore, this whole region is the one we want. Someone said one is easier. Do we want to do dy dx or dx dy? It's actually only ask preliminary question. If I do it dy dx, can I do it with one integral? And then follow-up question, if I do it dx dy, can I do it with one integral? So yes, for dy dx, you can do it with one integral, so we'll use that. And then can I do it with one integral doing dx dy? That one is no, because you can see the left function changes, which we'll deal with in a second. So limits. So here, put down the function. What are the limits for y? So the lower limit is x squared, and the upper limit is x plus 2. And the outside limits are points apart, -1, 2. So that's the answer for part A. And this is what I'll probably do tomorrow, instead of having a separate one, then have you actually do one of the integrals. Since you've done this, I'll go through the steps and you'll just correct me because I can do it quickly. I assume you'll mess up. So let's see, this is about done over into the dx. antiderivative. And what do you get for a number? I say that definitely is true. Someone else get the same thing? I think that's what I got, but sure. But first, let me just double check. Someone else get 189 before I go back up here and redo it. Yes, okay, good. So let's try this dx dy, see why we didn't really want to do it that way, although I would have too much more. So here you can see right here is where it's going to change, because below that line, the left function is the x squared. Above that line, the left function is the x plus 2. So let's split it up. So on below, so down here, what is the left function? Draw our typical horizontal line. Ask where we hit. On both sides, we hit y equals x squared. It's just on the left, on the right, we're going to get solve and get square root of y. What are we going to get for the bottom limit? Just a negative. And that goes from the bottom 0 to this line, which is 1. And then from this line to here, so from 1 to 4. Now the left function is the x plus 2, which is x equals y minus 2. And on the right, it's still square root of y. So yeah, that's probably not the way you want to do it. So that's the other way. So any questions on either of those setups? Page 2. Okay. So, oops. Okay, how about now? Can you hear me now? Hello? Okay. As I was drawing, I accidentally put my hand on the the microphone and muted myself. Sorry about that. So we have y equals 2 minus x, which is x plus y equals 2. And then we have y equals 2 minus 1/2 x, which is x plus 2y is equal to 4. So we have those two lines. So I draw those two. So x plus y equals 2. So we can actually draw a straight line. Oh, almost. So I draw those two lines. We also need, so in the first one from 1 to 2, actually, this isn't too terrible. We're going from 2 minus x, so we're going from x plus y equals 2 to 1. So I draw y equals 1. And not completely obvious in my graph, but that's at the point 1, 1. Same thing here, it's not completely obvious. It does hit right there, so it does have that little piece. And for the second one, we're going from 2 to 4. And so that's this piece. So it is that region there. Oops. So what is the left function? It's actually, you've already all done this. So what are the limits for the outside? And then I'll ask you the question. So the limits on the outside are, yep. And on the inside they are, yep. Yep. So usual thing we draw for this, we draw the horizontal line. Where does it hit on the left? Where does it hit on the right? Solve it in terms of x. And get that. So any questions on this? Oh, thank you, yes. I think I said 2 minus y, but you are correct. So any other questions on this? So last one. And this would be, so this is only after we do it, if you want it on, is here we draw it. So it says we have the region x squared plus y squared is equal to 25. Our usual circle holder. And above y equals x. So no, as usual, my lines are not correct. And above, so it's this whole region. And now I want to rewrite this using polar coordinates. So what do we get for the function? So what does 2xy become? Or q cosine sine. Yep. So I'm going to split it up. So we have the 2 r cosine theta, r sine theta, and we have the usual r dr d theta. Of course, it's 2r cubed sine theta cosine theta. And what are the inner limits? Start with the easier one. R goes from 0 to 5. for the outer limits, we need the two angles. Lower angle is, we just did, right? So pi over 4 and then pi plus pi over 4. Okay, so get that. So if I was going to have it on, this would be the level of one that's on the quiz. As in nothing where it's too elaborate. I just have you set up so you don't have to actually do the integral. So the question is, right, and so now we're deciding if 3 is okay. So this was the actual quiz in the spring, quiz 4, same thing. And then the question is, the possibility is either have it like this, with obviously different questions, or instead of 3, there would be another one such as 1 where you just set it up. So another one. So this part. So that's just this. So 2xy. And that is just straight. X is equal to, the reason I left it out is x is r cosine theta, y is r sine theta, and this you always get when you switch from dy dx. So the extra r is always there. So I could do a poll, but let me just ask, is anyone, so if it's this level, is there anyone who doesn't want this on it? And I said that if this isn't, then there'd be another one like 1. Yep, okay, so therefore, quiz is sections 3.1, 3.2, and 3.3. Yeah, so as I said, it's not going to be like we did the one yesterday where it was mixed up and also the intro wasn't necessarily that nice. It'll be like this where it'll be just a circle and an angle. So like the one we did just before, y equals x or y equals 2x or y equals 5x or something like that. Oh, yeah, I forgot about that. The TA said that he had 2 presentations yesterday or Monday, so he said he'd do them this afternoon. Sorry about that. If you took it with me, you already have them up there, but yeah. Yeah, I try to make the numbers turn out. As you noticed from the one test, I messed up one of them so that the points were something like e squared, 12e squared, and 12e squared plus 2 or something like that. But I try to make them so they're a little bit nicer than that. Oh, so this one? Okay, so pretty much what I just did is we had these 2 lines. So I graphed the 2 lines. So pretty much I just graphed everything. So I graphed those 2 lines. Those are the 2 lines given. And then I graphed y equals 1. There's y equals 1. And then I just noticed, oh, it's going from, that's the point 1, 1 to the point 1, 2, which are the limits of this, which means I didn't have to do anything else. And then I noticed that this is the points 2, 1. This is a point 4, 0. Again, I didn't have to do anything new because that gives the limits there. So therefore, this whole thing is it. So pretty much, I just graphed the x plus y equals 2, the x plus 2y equals 4, and y equals 1, and then just notice that everything else filled in the limits. If the second integral had been 2 to 3, I would have noticed, oh, I don't go all the way, I just go to there. But here it worked out that it just, the limits were exactly with it. So pretty much you're just graphing all the functions. So if you really want to do all of them, you could graph y equals x plus y equals 2, y equals 1, x equals 1, x equals 2, y equals 0, x plus 2, y equals 4, x equals 2, x equals 4, and you'll just notice, oh, it's not, the outside limits weren't really giving us anything extra. Any other questions? Wait, so Allison, if you think about it, so let me go back to 1, although my answers are gone. But you're saying, so in the 1 order, we got -1 to 2, and x squared to x plus 2. Okay. And if I do this, at the end, I'll get the number, 189. Don't even worry about thinking about it. So you're saying, why can't we just do this? And now think about it. In this one, since at the end we're going to be plugging these in, am I going to get back a number answer? No. So the idea is we always need, so it is always true that as you work your way out, you're losing variables. So in the innermost, there are functions, perhaps. They can be constants, but in general, they can be functions. And as I move out, I lose a variable. So on the outer one, they should always be constants. So outer limits should always be constants because the integral is giving us a number, which remember in this case is the volume under the curve. So it's a volume. So it doesn't make sense to get a variable answer unless, so for example, if I said this from A to B, so it's kind of sort of variables, but we should always be getting a number answer. And then for Gwyneth, so tomorrow, yeah, so tomorrow it'll be a fairly simple one where all the limits are just constants of some sort. Okay. So let me quickly, I would have to tell you. So in some ways, the reason I told you is that in this case was, so if I go back here, I say that it's half the circle, is just, you just draw the line, right? And if you draw the line, then you'd see it just keeps going. Unlike the one we did before where I said we're just doing the first quadrant, we're saying, no, we're not looking at the full circle, just that first quarter. So let me quickly do the beginning of the next one. And in some ways, the reason I want to do this is that way, when tomorrow we do the usual half hour of stuff that isn't on the quiz, it can be stuff that is partially a review for the quiz. Because now we go into 3 dimensions. And for the usual intro, let me just do an example. And with the example, you'll see why tomorrow this will make it so that it's at least a partial review for the quiz. I'm not very good at 3-dimensional ones, but so there's our region. And in some ways, one way of thinking about this is based on something you can picture, which is we now have 4 dimensions. And we have the, say, w is equal to the function in terms of the other 3 variables. And so in some sense, this triple integral is going to give us the hypervolume of the 4-dimensional object. But a better way of thinking about it is if you pretend this is, which we'll get to in a couple sections, if we pretend this is the density and we integrate over this region, what we would get is the mass of that 3-dimensional region. So that'd be kind of a typical thing of why we would integrate a function over 3-dimensional objects. And let me talk about how you would do this, which is part of it is the same thing as what we just did, which is just like in 1 variable and 2 variables. What we're looking for is we're going to integrate from the bottom function to the top function. So we have this x, y, z, and then we start off with z, dy, dx. As with the 2 variables, it doesn't matter which one you do, but let's do it this way. So if I'm starting with the z, what I'm looking for is what is the bottom function and what is the top function. So here, the bottom function is the x squared plus y squared, and the top function is 9. So in some sense, nothing different. It's just that now we have 3 possibilities. We could start with dy, in which case we'd have left and right. We could start with dx, in which case we'd have back and front, but we're always going from smaller to larger. And notice this one has 2 variables, and as I said in the last one, as we work our way out, we're going to keep losing variables. So in the next one, it'll be just in terms of x, and in the outermost one, it'll be just in terms of constants. This part, the next part, is where it gets a bit more confusing. Luckily, in this text, we don't do anything more complicated. But the next part is we have to figure out what region are we integrating over. And to get that, what we're asking is, if I look at this from the front, so you can think of it in 2 ways. If I look at it from the front, what does the biggest thing look like? Or if I take this 3-dimensional object and squish it down into the xy plane, again, what does it look like? So we're looking for what's the biggest it looks like from above. And so in this case, you can see, well, this one is pretty easy because it's getting bigger as I go up. So the biggest it is just right at the top. Sorry. It's just right at the top. So therefore, our picture is just x squared plus y squared is equal to 9. And then these outermost ones are, what are the limits if we integrate over that? So I'm going to do this in this straightforward way with the rectangular, and then you'll tell me that that's silly and how I really should do this and why it's going to be a review for tomorrow. So we have the x squared plus y squared, 9, 6yz, dz, dy, dx, dz, that is. And so here I'm looking for what is y in terms of x. So this is, I'm going to solve this in terms of y. So at the bottom, I get the negative square root, and at the top, I get the positive. And left limit, that's true for the full circle. So it goes from -3 to 3. So why is this silly? What coordinate system should I be using here? Polar, right? I'm doing circles, so why I should really be doing polar coordinates. So let's redo this in polar coordinates, which officially in 3 dimensions become cylindrical. But notice that means if I do cylindrical tomorrow as an example, I'm basically reviewing polar coordinates. So the x squared plus y squared becomes r squared. 9 is still 9. Here we're doing polar coordinates. The circle is x squared and y squared, so therefore z we're not going to change, but we're going to make y into the r sine theta. Z, as I said, is staying the same. We, as always, get our extra r, the r times dr d theta. The dz is just going to stay there. And now what are the limits in terms of the circle? So the limits for r would be, which Maxwell gave me long before, 0 to 3. And for theta, the limits would be 0 to 2 pi. So this extension is what happens if we're going into 3 dimensions. It's basically polar coordinates with an extra variable, but it's called cylindrical. So this is the idea, which is first step is look for what's the smaller to larger function using all the variables, and then to compress that down into one of the component axes, so either the xy plane or the xz plane or the yz plane, to get into 2 dimensions, and then use the 2-dimensional limits to get that. For me, that middle part is the hard part, which is seeing what it looks like if you compress it down into one of the planes. But as I said, luckily this text doesn't do any of the more complicated ones, so it's not too bad. So this is what we'll start with tomorrow, which is we'll do a couple of these where we set up some triple integrals. But obviously it's not in the quiz. And as I said, the nice thing is by doing this, I can do ones where part of it's going to be polar coordinates, so partial review. And so that's the usual really quick intro. Any quick questions about this? Okay, then usual thing, if you're ready, we're done. I'll stick around if you have questions. I'll stop recording. And again, tomorrow, first half hour is the new stuff and then quiz.